Okay, so now we're going to look at what can go wrong in a significance test. And so when things go wrong, we typically call that an error. And there are two different types of errors that we can have in a significance test. And we call them type 1 and type 2. But first, let's talk about that we really hope that things will be correct. So really, when we are making, when we're doing a significance test, we have two options. Either we reject HO or we fail to reject HO. And we compare that to the idea of what's really true. Is HO true or is HO false, which means our HA is true. And so we've got two different things here. So if I reject HO, but HO is true, then we get a wrong answer. We were wrong in our test. And we don't want that to happen. So we want to minimize that probability. Now, if we reject HO and HO is false, then we did a good thing. And we want that number probability to be high. Now, if we fail to reject HO and HO is true, we're correct, and so we're okay. Even though we did it and we didn't truly, seems like we didn't get anywhere because we didn't prove something false, but our answer was correct, so we were good to fail to reject HO. Our suspicion was false. But if we fail to reject HO and HO is truly false, then we're wrong. So we've got two different ways to be wrong. We reject HO when HO is true, or we fail to reject HO when HO is false. And I call this the double F, because we fail to reject when false. And so these are two types of errors. Now the type 1 error is the very first error that we had. So this is type 1. And that's when we reject HO when HO is true. It's the 1 in a million case. Like, yeah, there is a 0.0001 probability that would happen, but there's still a chance that it could happen. So kind of like winning the lottery. There might be a 0.00000001 or a 1 in 74 million chance that you could win the lottery, but someone wins the lottery, don't they? So you could be that rare 1 in a million case. And so that's what happens right here. That rare 1 in a million, when the probability was so low that we rejected HO, but really it was the 1 in a million. And then we have the type 2 error, which is why I pointed out this double F. We failed to reject when it was false. And that is our type 2 error. Two Fs, type 2 error. Failed to reject was false. This is where our sample probably wasn't accurate enough to give us that probability to show that it was false. So based on our sampling distribution, it just wasn't enough evidence at that point. Okay, so we're going to look at explaining what type 1 and type 2 errors are. So the manager of a fast food restaurant wants to reduce the proportion of drive-through customers who have to wait more than 2 minutes, which is good because people hate waiting in the drive-through, to receive their food once the order is placed. Based on store records, the proportion of customers who had to wait at least 2 minutes was 63%, or as a proportion, 0.63. To reduce this, the manager assigns an additional employee to assist with drive-through, so it costs more money, but it keeps people happy, so they're more likely to come back. During the next month, the manager will collect a random sample of drive-through times and test the following hypothesis. So, will it change? So no difference, it stays at 63%, but he's hoping that the proportion that has to wait is less than 63%. So he's hoping to minimize that. So describe a type 1 and type 2 error. So I typed this up so it goes faster. So type 1 error means that I reject HO when HO is true. So I reject, so I was saying that it's not really 63%. In fact, it's lower than 63%. When really it's not. So determine the proportion of customers that wait more than 2% 2 minutes to get their food is less than. So we determine, kind of like HAA is true, when really it's not true. Really it's 0.63 or higher. So really nothing's changed. So you spent all this money to get someone to work the drive-through, and the same amount of people are waiting forever in the drive-thru. Now type 2 error is going to be the opposite. So we're going to fail to reject. So fail to reject means that we assume that there is no change now. So we determine there's no change. The same amount of people wait 2 minutes to get their food, but really it is less. And so what's the consequence of that? Well, that person may get fired because they were hired to make things go faster, and they actually are making things go faster, but we don't have evidence of that. And so the poor guy loses their job. Okay, so now we're going to practice. A nationally known gardener claims to get 25% more blooms on a rose bush during the summer season. We've seen this problem. We did the HO, HA. So we claimed before HO was that the mean number of blooms was 34. Oops, those are dots. And then we're hoping that the mean number of blooms is actually more than 34. So we're hoping that that's going to help us get more rose blooms on our bush. Describe the type 1 context. So I'm going to reject HO. So I reject HO, which means I determine that HA is true. So determine that there is more than 34 blooms. But we're wrong, so when there is not. That's probably comma splice, don't need that in there. So what's the consequence of that? So we think this food is working, we're paying all this expensive money for this food for our plants, and really it's not doing anything. So sometimes you just have to interpret what the type 1 error is, and sometimes you have to do consequences, and sometimes you have to do both. So it's a good idea that you practice both so you really understand what that is and get practice thinking like that. So determine that there is more than 34 blooms when there is not, and then we're going to pay money for a product that isn't working. So type 2 error would be to fail to reject. So fail to reject our HO, which means determine that HO is true. So determine that there is still 34 blooms on average, when really there is more. So determine that the product doesn't work when it really is, or maybe we throw away a really good product. So there might be a consequence. Or we tell everyone that the product doesn't work when it really does work, so we look silly. Okay, next one, VitaBlend, a new brand of vitamins, claims in a radio spot that the people who take VitaBlend vitamins wake up refreshed. So our null hypothesis is within 5 minutes. Okay, so we assume that on average people get ready in 5 minutes. We're hoping that using this VitaBlend that they get ready in less than 5 minutes. Describe a type 1 context error. So type 1 error is we reject HO. So we reject 5 minutes and we determine that HA is true. So we determine that we are ready, and that's more like waking up all nice and refreshed and ready to take on the day. So that's why I do the quotation marks. Determine that we are ready in less than 5 minutes. When really we're not. What's a consequence of that? We keep spending money on a product that really isn't working. Okay, type 2 error, so fail to reject. I fail to reject that, so we assume that it still just takes us 5 minutes. To be ready for the day, when really the product is working. It's almost like optimist versus pessimist. We're an optimist, woohoo, it's working, when really it isn't. And pessimist, it doesn't work, when really it is. Consequence, maybe we throw away something that's really working. We never give it a real good shot when something that may really help us out. Stuff like that. So give up on a product that works. There's a consequence. And people's consequences can be different, but they have to be a realistic consequence that fits what you determine to be true. Okay, so next one, school principals not pleased with first semester exam scores. First 2 period history classes, so HO on this one was that the mean scores were 72. HA was that we wanted those scores to be higher. So the first one, we reject the null hypothesis and determine the scores are higher. And of course, this is on average. The average scores are higher than 72, when really they're not. So what's a consequence of that? Well, we think that team teaching is working when really it's not. So keep using a teaching tool that's not really working. So continue. A teaching tool that doesn't help. Okay, describe a context type 2 error and its consequences. So fail to reject. So I fail to reject HO. So we assume that the scores are the same. Determine that the average scores do not change. When really they do. So what do? We give up on a teaching tool that is really making a difference. And so a lot of people will ask me, well, why is it important to know the difference between type 1 and type 2? When you're planning something, you really want to think about the type of errors. And usually you can minimize one. You can't always minimize both. If you can minimize both, try to as much as you can. But if you can minimize just one, you want to minimize the one that's going to make the least damage. So if you could tell, well, what are the errors? What are the consequences of the error? And you know what? A type 1 error is way more dramatic and drastic and has way more consequences than a type 2 error. So I'm going to make sure that of all things, I'm going to make sure my type 1 error is as small as possible. So that way, I have less likely chance that I'm going to make that error and less likely chance that this dramatic consequence will happen. And so it's all in the planning of your study beforehand. So heading into election, Jack needs 50% of the vote. Okay, so here our HO was P is 0.5. We're hoping, so HA, that the proportion is greater than because he wants to win. So type 1 is we reject the null hypothesis. So we determine that Jack has a majority of the votes. When he doesn't. So what's a consequence of that? He thinks he's going to win and he really doesn't. He gives up because he's like, oh, I've got this in the bag, and doesn't put that extra oomph that could actually help him win. Lots of different consequences, but I think really thinks he's going to win and doesn't. Doesn't put in any extra effort to try to win because he thinks he's got it in the bag. Describes context type 2. So fail to reject. So I fail to reject HO, which means determine that Jack does not have majority vote. When he really does. So maybe he goes out there and he's all like, man, I've really got to do something to wow them. So he puts together this really expensive commercial and puts it out there to try and win voters over. And he pays all this money when really he had enough votes to begin with, so he didn't need to spend all that money. So spends lots of money trying to get more votes when he doesn't need to. And so this brings me back to which consequence is more dire? Oh, he thinks he's going to win but doesn't. Yeah, it's not that big of a deal. But when you think about all that extra money and stuff like that you'd spend trying to get more votes when he doesn't need to, that's a lot of money on the line. So that seems like a bigger thing. So always have to weigh those consequences when you're planning something out so you can plan it correctly. Because you don't want to do a study, spend all that money going out there and studying the information, and then have it not go right because you didn't plan out the study very well. Okay, error probabilities. We can assess the performance of a significance test by looking at the probabilities of making these two errors. So what's the probability that I reject HO when HO is true? Well, this type 1 error is actually the same as our significance level, alpha. So if our significance level is 0.05, there's a 5% chance of making a type 1 error. Now a type 2 error is the probability that we fail to reject when HO is false. Now type 2 error is way trickier. So type 2 error occurs when we fail to reject a null hypothesis that is really false. But there are many possible values of the parameter that satisfy that alternative hypothesis. And the true parameter value determines that probability, because remember, that's how we get that probability curve. And so that value adjusts, and if we don't really know what the true parameter is, it's really hard to calculate that. Now we can calculate the probability that a test does reject HO when the alternative is true. Again, that probability is called the power of a test. So this is a type 1 error, this is a type 2 error, and we can calculate this, that we reject it when the alternative is true. That's our power. This is our true correct conclusion. We can calculate that, and that's called power. But calculating power can only be calculated when you know the true population value, which again you rarely know. We can test out different values and we can know what affects power. So we can always try to increase power, which will decrease our type 2 error. Because the probability of a type 2 error is 1 minus our power. So the higher the power, the lower the chance of making the type 2 error. So if we can increase power, we can decrease this. And then depending on stuff, this is our alpha, so we can, if we want to decrease our type 1 error, we decrease the alpha. We make that way small. And so we've got some things that can help out with that. So low power means the null hypothesis is unlikely to be rejected and the experiment is inconclusive. Which means that really we did all that work for nothing. So what affects power? So this is just kind of an idea of how the things work. This is our type 1 error. The probability is alpha. This is our power. We proved our claim wrong. We did good. This is an inconclusive test because our claim was true. And this is our type 2 error, which can be calculated by 1 minus power. And since we usually can't calculate power, again, we're looking at what affects it. This is what we want. We want higher power. How do we get higher power? We can increase our significance level, which actually decreases when we increase our significance level. That is increasing type 1 error, because our significance level is type 1 error. So we have a higher power, which means we increase type 1 error. We increase sample size, which is increasing n. We can decrease standard deviation. How do we decrease standard deviation? Increase sample size. Increase the difference between our null hypothesis and the true population value. Usually we don't know the true population value, so... And then use a one-sided test. So test for less than, test for greater than, but do not test for neither, which is actually testing for both. So how do we lower power? Again, this is what we don't want. We don't want to lower our power. That's going to increase our type 2 error. Decrease our alpha, which decreases type 1 error, because alpha is type 1 error. Decrease sample size, increase. So these are all opposites of what's in green over there. Okay, so the manager of a fast food restaurant wants to reduce the proportion of drive-through customers, blah, blah, blah. We've talked about this one. So now he wants to change some aspects of the study. And he wants to do that to figure out how's that going to affect the power of the test. So to reduce the possibility of type 1 error, so reduce type 1, means he's going to reduce alpha, which is our significance level. And he's doing this because he wants to avoid the possibility of unnecessarily paying an extra employee. Again, a consequence. The manager reduces the significance level from 0.1 to 0.01. How is that going to affect our power? So if we decrease our alpha or decrease type 1 error, so decrease alpha, decrease type 1 error, that's going to lower our power. Or as I like to write, is lower power. Because I'm lazy. To justify additional cost of an extra employee, the manager decides that the true proportion must be reduced to at most 0.53. So now these values are changing to 0.53. So I'm changing the HO to 0.53. So that means I am increasing the difference between the null and the population. So when I look back here, if I increase the difference between the null and the true population, that's going to give me higher power. Which is weird because, again, as we increase power, we are going to increase type 1 error. But as we increase type 1 error, we decrease type 2 error. So it's give and take. To get faster results, the manager reduces the sample size. So my sample size, n, is going to go down. So how's that going to affect our power? Well, increase sample size. No, we're decreasing sample size, so it's going to lower our power. And so you're going to find multiple choice questions dealing with that. And even free response. Like, if I do this, how's that going to affect the power of my test? And so you will find this on your Chapter 9 test, so I highly recommend finding a way to study this relationship in some way or form. Okay, planning studies, determining sample size. So, again, sample size affects a lot. If you insist on a smaller significance level, so a smaller alpha, then you really need to increase your sample. Because a smaller significance level requires stronger evidence to reject the null hypothesis. So the more information or the more people you have in your sample, the more likelihood you are to get a smaller probability, because it tightens up that, it makes a distribution from here to be tighter. So less spread means there's more likely that we can meet that. Practical importance. At any significance level and desired power, detecting a small difference requires a larger sample. So if you want to detect a very small difference, you need to have a lot more people, which is more expensive. Power. If you want a higher power, such as a 99% rather than 90%, you need a larger sample. So really, you can't go wrong with a larger sample. A larger sample can help decrease your errors on both sides. That's the one thing. Increasing n will decrease T1 and it will decrease T2 because it increases your power. And increased people will decrease T1, which is really weird because typically if you decrease this, you increase this. But only with sample size does it help decrease both types of error. Okay, and that's it for today.